Now that we've refreshed our memory, let's rethink it. We'll go back to Calc 1. The graph of a function, but we'll think of it as a point in and a point out, input space, output space, and a slope. So instead of slope, we want to look at slope vectors. Unit vector input, derivative scaled vector output. The input then is a ordered pair, a position and a vector, and the output is kind of an ordered pair, a position and a vector. Whereas before, we thought of just numbers. F of x was a number, f prime of x was a number. Now we want to think of it as a point and a vector combination. Going to a point and a vector combination. So these are vector spaces located at an origin point that's not the origin of the space. Put two of these pictures together, one in x, one in y, for the Calc 3 case. Our function has a tangent plane and the two standard tangent vectors in the coordinate directions. Repeating the construction we just did, we get our two tangent vectors. One in x and one in y. Given any other vector, it's a linear combination of these two. And we introduce the dot product notation with the gradient. Input space and output space. Input point and output point. R2 input, real output, and the function that takes one to the other. At that xy point, I have two vectors now. One vector in the x direction, which gives me a scaled vector in the output. One vector in the y direction, which gives me a scaled vector in the output. So linear combinations are preserved. Instead of dot product, instead, let's write it as inner product. Well, then this is a matrix. Putting it all together. One two-dimensional input, one-dimensional output. I'm at some point, going to some point. At that point, I put in my basis vectors. Generating a copy of the space centered at my input point. Those vectors go to the output space. Now we're going to put two of those pictures together. So now I have an R2 to R2 mapping. Input point, output point. Just looking at the single basis vector, that goes to a vector in R2, this basis vector, another vector in R2. These are our x partials and our y partials. This defines a linear transformation. The columns of the matrix for that transformation are where the basis elements go. Our function and our derivative function.